Hey there, discrete math fans. I'm delighted to let you know that we'll be starting chapter 10 today, graph theory. And so 10.1 is just a series of definitions and activities to kind of introduce you into a new world of graphs. Thus far, probably in your mathematical life, you've thought of graphs as functions where for every x there's one y, and you've done vertical line tests and you've looked at relationships and all that sort of thing. But think no more like that, because graph theory is totally different. We define things differently. The applications are different, and it's really going to be useful for you. I think it's fun and interesting. If you go to grad school into computer science, you'll do lots of graph theory, and I think you're going to like it. People usually do in this course. So I do have a PowerPoint. It's on Foxtail, and I'm going to share with you a little bit from that, and then I'll bounce back and forth my whiteboard a little bit. But thought that I would start out with a scripture from Colossians 3, just for your edification and inspiration. Let the peace of Christ rule in your hearts, since as members of one body, you were called to peace, and be thankful. Let the message of Christ dwell among you richly as you teach and admonish one another with all wisdom through psalms, hymns, and songs from the Spirit, singing to God with gratitude in your hearts. And whatever you do, whether in word or deed, do it all in the name of the Lord Jesus, giving thanks to God the Father through him. In this time of uncertainty, maybe fear, disappointment, when we get back to our true north, when we get back to the things that really matter, we see that we're served well by just trusting that God is in control. None of these uncertainties were uncertain to him. There are no surprises. There's nothing beyond his ability to control and work together for the good of those who love him. And so my prayer is always, help me to love you. Help me to overcome my unbelief. Help me to trust you more. And I think that does make all the difference. Anyhow, let's bounce right into graph theory 10.1. Graph theory for kids. I think you guys are kids. You're going to have a good time. We'll just play with some of these problems. Quote from our book: the whole of mathematics consists in the organization of a series of aids to the imagination in the process of reasoning. I love this. So often it's just a little diagram that unlocks a tremendous mystery. In mathematics, we are looking for all those little tricks to help the imagination in the mind better understand the problem, that we might find routes to the solution. And that's really what graph theory is. It was born out of problems, not sort of a theoretical idea, but birthed by, I guess, Euler in this Königsberg bridge problem, which you'll see in 10.2. And it is amazing how many different kinds of applications there are to a pretty simple little idea that can get complex very quickly. So let me just show you a few of the applications. Basically, we're talking about any diagram that represents scenarios, combinations, possibilities. We've actually been looking at graphs all semester. We've been making trees and looking for probabilities and different possibilities, routes from one place to another. But in what other applications are we interested in? Routes and locations. Essentially, a graph is really just a series of dots called vertices or nodes, and then connections between those dots called edges. So you can see that networks make use of graph theory. Brain research, very interesting in terms of how electrical pulses and nerves and all of that interesting stuff in our head sort of follows patterns, and graph theory can lead us into some insight there. Of course, flowcharts and organizational movements. I like this slide. The World Wide Web, all sorts of connections. Facebook. So if you can learn to make lots and lots of connections, you can make billions of dollars. Electronic circuits, networks with roads, flights, communications, city planning, locations, and connections between those locations. It's in the DNA of life itself, biological networks. But essentially, what are we trying to do? We're trying to create a series of dots and connections. And sometimes we have directed graphs. This graph is a directed graph. You can see there are arrows in it pointing from one place to another. So dot 8, vertex 8, you can get to vertex 1 from vertex 8 with a distance of 5. So this is also a weighted graph. This is a weighted directed graph right here. And in one of these, you can't actually go backwards. I couldn't go from 1 to 8 via this route because it's not allowing it. So that's a pretty complex graph right there. Another interesting thing about graphs is we don't really care how long the edges are, and we don't care how straight they are. We care about their weight, if they're weighted. We care about their direction, if they have a direction. And we care about what they connect, what vertices they connect. And based on those different interesting components, we create problems and solve them with graphs. One of the things that we'll be very interested in with graph theory is what's called the degree of a vertex and the degree of a graph. So if you look at a graph and you want to know the degree of a vertex, that's really just how many edges either come into it or go out of it. So this vertex right here has a degree of 2. 2 edges go into it. This is a non-directed graph. This vertex right here would have a degree of 1, 2, 3, 4. And the degree of the graph would be the sum of the degrees of all the vertices. So we'll be very interested in the degrees of vertices, particularly if they're odd or even, and the degree of the entire graph, the sum of the degrees of the vertices. But before we get into too many details, I thought we could just set up a problem and solve it with a graph. An organization wants to set up teams of 3 to work on a project. In order to maximize the number of people on each team who had previous experience working together successfully, the director asked the members to provide names of their past partners. I have some information on the next slide, but what we'll be trying to do is make a graph, and that is a series of dots or vertices. Each dot will represent a person, and then edges connecting dots of people that have worked together successfully in the past. So what I'd like you to do is I'd like you to take a look at this information and go ahead and pause the video, make a graph of the information, and then try to make a recommendation on 3 teams of 3 to optimize the people who have worked together successfully before. So go ahead and pause the video, make a graph, and then we'll see where that goes. Well, here's my graph. Basically, I just made connections between all of the people, and of course I abbreviated their first names. But in looking at this, maybe you decided that the best way to make teams where partners were optimized, in other words, people had been together before are together again, might be to take this triangle here, Bev, Flo, and Kai, and just put them on a team. That'd be okay. And then another team of 3 might be A, D, and E. That might be a decent team. And then having I, H, and G, Hal, Gia, and Ira on the same team would be the best way to organize 3 teams out of all of those people. So that might be a way of visually making a decision quickly and easily, because we could see who's been connected and who hasn't. Now, verbally, I'll share my screen back with you again. You might use logic like this in your strategy. But all the while, the strategy probably was illuminated because you were able to look at the diagram or the graph. Bev, Kai, and Flo, they've worked together before. We put them in a group. We take that triangle out. Hal and Ed are on the same team. If that were the case, then either Gia or Ira would not have any past partners, so that would be a bad idea. So put Hal, Ira, and Gia on a team. leaving Anna, Dan, and Ed for the last team. This is in the book, and I think it's pretty straightforward, but it's a great use of graph theory to solve a problem. Probably you'd get the same thing if you didn't make a graph, but it sure makes the problem easier and probably more quickly solved. So a few definitions. A graph consists of two finite sets, a set of vertices and a set of edges. This would be the vertices of G. E of G is the edges of G. The correspondence from edges to endpoints is called an edge endpoint function. I'll give you an example of one of those in just a minute. An edge with one endpoint is called a loop. So you can go from a dot back to yourself. You can just wrap back around to it, and we'll see a few examples of that. And we can have two or more edges with the same set of endpoints. If we do have that, we have parallel edges. A few other definitions. An edge is said to connect its endpoints. Two vertices connected by an edge are called adjacent. A vertex that is an endpoint of a loop is said to be adjacent to itself. An edge is said to be incident on each of its endpoints. Two edges incident on the same endpoint are called adjacent. Adjacent just means right next to. You can have edges right next to each other. You can have vertices right next to each other. And a vertex where there are no incident edges would be isolated, just a dot somewhere out alone. So here are some graphs, graph 1, 2, 3, and 4. We want to take our new terms that we just had, connects, adjacent vertices, adjacent edges, incident edges, isolated vertices, parallel edges, loops, things like that, and kind of understand them in a picture. So I'll just mention a few here. So here's a loop right here. And by the way, a loop actually contributes to the degree of a vertex. So this vertex down here, R, has a degree of 1, 2, 3, 4. That loop is contributing kind of on both ends of the loop. We actually have something going on right here. This little X, Y, V is kind of like its own little part of a graph. It's a connected component, which within these three things, there is connectedness, but you could actually take the X, Y, V, move it out, and it's a part of the graph, but it's disconnected from the rest. So a graph that's not all connected to itself is called a disconnected graph. We see elsewhere, we see some parallel edges. Where do we see parallel edges? Like going from, actually, like this one, F to D is an edge, but we don't have another single edge going from F to D, so those aren't technically parallel edges. To get a parallel edge, like C to D right here, would have to have another edge going from C to D. That'd be a parallel edge. Yeah, but these are sort of skipping edges in here a little bit. So go back to the terms if you want to and try to draw graphs. You can look in the book as well that make use of these words so that you understand the meaning of those words. Don't see any isolated vertices in here, but like an edge right here that's right next to another edge, they're connected by a common vertex. Those are adjacent edges. A and B would be adjacent vertices because they're connected by a common edge. Moving right along. Here's another graph. Oh, here's some parallel edges right here. Edge 7, edge 6, and edge 5 are all parallel edges. You got a loop right here. This edge endpoint function is just a function that gives each edge and what their endpoints are. And you can see we've got the degrees of each vertex and then the total degree of the graph. So the degree of the vertex, again, is how many edges come into it. So vertex V would have a degree of 1, 2, 3, 4, 5. The degree of V is 5. Interesting thing about graph theory is that a lot of graphs that look different, they might look terrifically different or terribly different, depending on your definition of the words, but very different from each other might actually be the same graph. Again, we don't really care about how long the edges are. We don't care about how straight or how curvy they are. We just care about what is connected to what. We could even have two different graphs that, that are named differently, but if we can say that they functionally do the same thing and have the same connections, and we could sort of name a vertex and then another vertex that corresponds to it in another graph, we could say those are isometric. That comes a little bit later in the chapter. But a couple of quick examples. I'll just stop my share here. So I could have a graph that looks like maybe this, and another one that looks like, actually, we'll make this part of the same graph. So this is one graph. This is graph one. And if I draw another graph that maybe looks a lot different, like this, there's no difference between graph one and graph two. They both have two vertices. Maybe these are named something and these are named something else, but basically, if you can make a one-to-one correspondence and say there are two parallel edges connecting these two dots, and those two are kind of their own separate thing, they're a connected component of the whole graph, and then the other part of the graph maybe has this sort of thing happening, just like this is happening. We don't care about intersections at all. We only care about vertices, defined intersections, I guess. So like this means nothing, this means nothing, unless I actually put a vertex there. And that would mean we have a series of other paths and different edges. But you can separate graphs out, you could stretch them out, squeeze them, make the lines short, make them long, make them curvy or straight. And those things are irrelevant, they don't really matter. Another way of kind of looking at it is I've got, say, this piece of string, and I've put 1, 2, 3, 4, 5 knots into the string. It's tied at the end. Just pretend like the end is just a separate knot. But there's a graph right there, a series of vertices at the knots and then the connecting edges. So the graph could look like that, or I could wrap it around like this. And that looks totally different. But as long as the knots are vertices and then the edges are the things that connect the vertices, it doesn't really matter that it wraps and overlaps, because an overlap is not another vertex. Like with functions, you have intersections, but with graphs, we have defined vertices and edges. So you can make all sorts of different shapes. And that graph is the same whether it's in this form or whether you sort of like reduce it and untwist it. Equivalent graphs. As I mentioned before, sometimes we have directed graphs. This graph is undirected. There's no arrows that point you from one to another. And if there are no arrows, it's assumed that you can pass in both directions. A directed graph might look like this, where you have an edge with an arrow and then another edge with an arrow. Some books actually just do like a bidirectional double arrowed kind of edge. So basically, we create the graph to serve certain functions, and if you can pass only one way or both ways, we can make note of that with arrows. It's an interesting little problem. You've probably seen ones like it in the book. Vegetarians and cannibals on one side of a river trying to get to another side of a river. And a graph really does help answer this question. It's a little bit more complex than the last problem about Hal and Ira, making sure that people were on teams that had been together before. So here we go. On an island, people are of two types, vegetarians or cannibals. Initially, 2 vegetarians and 2 cannibals are on the left bank of a river. Down here, you can see this notation: vegetarian, vegetarian, cannibal, cannibal, boat, slash. The slash is the river, and then there's nothing on the right side. So this would represent the initial condition. The boat can only hold 2 people, and we need to move 4 to the right bank safely. At no time can the number of cannibals on either bank outnumber the number of vegetarians. Draw a graph representing the possible scenarios. So we're not just saying solve the problem. We're saying make a dot, name it this. This will be your initial dot, and then consider alternatives that don't break the rules. Breaking the rules means we lose people. And by the end, the last dot would be kind of the exact opposite of this notation. You'd have nothing on the left with a slash and then everything on the right. So go ahead and push pause and see if you can make a graph that will do that. All right, maybe you got something like this. So I had two scenarios that I tried that weren't going to work out, and you probably tried some too. So you send a cannibal over with the boat, and then what can you do but send the cannibal back over and get to where you started? That's not going to be helpful. Or you send two vegetarians over with the boat, but then who's going to bring back the boat because they're going to get eaten? So that's not a good one. But there are scenarios. Actually, the graph of this shows 4 scenarios that'll work out. So you could say vegetarian cannibal stay, we send over vegetarian and cannibal, and then we could send a cannibal back because we still got 2 vegetarians, the boat's here, and then we can actually route this way or this way. So this does show 4 different correct solutions, whereby if you've got these vertices that begin where we have to begin and end where we have to end, then you can either take this route. So there's one. We can route there. Or we could route there. That's 2. Or we could take the lower route. Or we could take the lower route and wrap there. So you can see from this graph, there's actually 4 scenarios that would get you where you need to go. So the graph was really a nice way of organizing information into a diagram that helped us solve a problem. So hopefully that was fun. You can go back and look at it again if you need to. And I think we're just about done here, but let's make sure. Oh yeah, there's a few other things you need to know. These are just definitions and pictures associated with them. A simple graph has no loops or parallel edges. So here's a simple graph. We just have straight connections, but this one's not, because we've got an edge that goes from this dot to this dot and then another edge that also connects those dots. So those are parallel edges. That's not a simple graph. This graph over here has a couple of loops, so not simple. Complete graphs are simple, but every vertex has a connection in every possible way. So if we had 4 vertices and we made as many connections as we could, that would be K4. That's the complete graph K. K5 would look like this. This is called a bipartite graph. I'll show you an example of that in a minute. But regular K6 looks like this. K7, you can see we can get some really interesting pictures. And in the realm of graph theory, if you make things symmetric especially, you can get some really neat art and some really neat design. So not a big part of the chapter, but a little bit, and interesting, I think. There are also bipartite graphs. So a bipartite graph has a part of the graph that is not connected to each other, and then another set of vertices that aren't connected to each other, but there are connections across these sort of 2 separate subgroups of a graph. And these 2 graphs are the same. It's just that a rearrangement makes it more obvious that this is a bipartite graph. So it just means separating a graph into subgraphs, and they don't have to be of matching size, but they just can't be connected to each other. But you can make connections across those groups. You can have complete bipartite graphs. So this whole thing is a graph, but there are 3 vertices that aren't connected to each other, and then another 2 that aren't, but across the connections, every possible connection is being made. That's what complete means. Bipartite, again, is 2 groups of vertices sort of like each other. Here's some more complete bipartite graphs. This PowerPoint is on Foxtail, so you can go back and look at it if you want to. We can talk about subgraphs, which is just a part of a graph. So subgraphs might not include all the vertices, might not include all of the edges. Every graph is a subgraph of itself. We can also talk about spanning subgraphs. So spanning subgraphs contain all the vertices, but then these little dotted lines are edges that are removed. So this spanning subgraph includes all the vertices, but not edges, not some of the edges. And we'll talk more about that later, but that just introduces you to the idea. We talked earlier about the degree of a vertex. So we just talk about how many edges are going into a particular vertex, and that loops count twice. This makes sense then that the total degree of a graph is the sum of all the vertices of the graph. So you just add up all the degrees for all the vertices. And yet another example. This is important. If we have a graph, the sum of the degrees of the vertices is twice the number of edges, which if you look at a picture, makes a lot of sense because every edge in a graph, like this edge right here, contributes 2 to the degree. This edge right here contributes 1 to the degree at C, and then 1 to the degree at this vertex. So all you got to do to find the degree of a graph is to count your edges and then multiply by 2. It's called the handshake theorem. Makes sense then that the degree of every graph is even, right? Because if you take the number of edges, if the number of edges is even, times 2 is the degree, that's even. If the number of edges is odd, times 2 is still even. So in either case, the graph has to be even. So that's a quick, easy proof. And now if you want to, go ahead and pause the video, try to draw a graph with the specified properties or show that no such graph exists. Go ahead and push pause, try to make a diagram, and we'll be back in a minute to give a check on that one. So you probably noticed that the first graph there, if you added up the degrees of the vertices, you get 7, which is odd. It's not even. So the first one is impossible. You can't make it. The second one you can make. See, the second one, if you did something like, maybe like this, well, you have to have like 2 of the vertices had to have degree 3, 1, 2, 3, and then 2 of the vertices had to have degree 1. So that would work for that second one. And then the third one, you can't actually have a simple graph with the same number of degrees on the vertices because you have to have this parallel edge. And you probably tried that and it didn't work and it didn't work and it didn't work because it doesn't work. So fun questions, things you might do in your spare time just for fun, or so I'd like to think. How about a question like this? You'll see something like this in your homework. You've got 9 people, and out of those 9 people, is it possible for each of the 9 to be friends with exactly 5 others? So you might represent this with a graph, 9 dots, 9 vertices for each of the people, and then you try to make connections of friends. And every time you draw an edge from one friend to another, well, you'd need to draw 5 lines into each vertex, and that would represent exactly 5 friends. But if you think about that, then the degree of that graph would be 9 times 5, which is 45, and that's not possible. So you could try and try and try, but sometimes it takes a theorem, like the handshake theorem, to tell you this is not possible, and that one's not. So you'll see that in the homework. I think that this would be an easy proof. We can talk through it verbally. In any graph, there are an even number of vertices of odd degree. Then I guess I would just say, if there were an odd number of vertices of odd degree, an odd times an odd is an odd. And so that would contradict the handshake theorem. So you can quickly prove that if you want to. And that's sort of lots and lots of different definitions and an introduction to graph theory. I'll catch up with you in the next video, 10.2, where we will define movements in a graph. Take care.